Hello everyone, this is the presentation for paper, Semantically-Aware Object Coordinate Space for Category Level 6D Object Pose Estimation under Large Shape Variations. This is a work from National University of Defense Technology. 6D Object Pose Estimation is an important computer vision task. Different from instance-level object pose estimation, which predicts poses for instances that have been trained during training, category-level pose estimation requires predicting poses for novel instances of the same category. Most existing works on category-level pose estimation are based on the canonical representation of normalized object coordinate space. Given an unseen object instance, these methods learn to map between the camera coordinate and the NOCs from which object pose can be estimated. However, when the category contains instances with large shape variations, NOCs-based methods could be inaccurate and less robust. One reason is that the canonical representation of NOCs, which is induced by rigid transformations, is not semantically coherent. To tackle this issue, we propose semantically aware object coordinate space, a new canonical representation for category-level pose estimation. SOCS is built by warping and aligning the object instances guided by a sparse set of key points with semantically meaningful correspondence. Compared to NOCs, SOCS is more semantically coherent, allowing accurate pose estimation under large shape variations. Here are the details of our method. We first introduce how to build SOCS from a set of instances in one category. Given the instances of a category in the training set, we generate the categorical average shape by using a pre-learned autoencoder. We then detect semantically consistent key points in all instances. Afterward, we compute the dense correspondences between the average shape and each instance using a 3D thin plate spline warping function, achieving fine-grained non-rigid coordinate alignment. As demonstrated, the proposed SOCS is more semantically meaningful than NOCs, facilitating the learning of correspondence for instances with large shape variations. To learn the dense pointwise mapping from the camera coordinate to SOCS, we propose a multi-scale coordinate-based attention network. The network contains two main components, aggregation layers and propagation layers. The aggregation layers are responsible for extracting features of the input points at multiple resolutions. The propagation layers are utilized to propagate the extracted features from the input points to any query point in 3D space. As a result, the network is able to estimate the SOCS value not only on the input points but also on any query point in the camera coordinate. Specifically, the feature propagation is achieved by employing a cross-attention on features between the query point and its k-nearest points. We then describe how to obtain the query points. We tried 3 different sampling strategies during training: sampling on the input points, sampling near the object surface, and sampling in the whole 3D space. We empirically found the last strategy outperforms the others. During inference, we crop the RGBD image based on the detected object and generate the point cloud. Then, we densely sample points in 3D space around the input points, and extract their features with the multi-scale coordinate-based attention network, predicting the SOCS for every sampled point. The object pose and size can be estimated with an optimization function. We use standard metrics to evaluate the performance on 2 datasets, NOCs Real 275 and ModelNet 40. On NOCs Real 275 we found our method outperforms the NOCs-based baselines. This reveals the necessity of both the representation of SOCS and the proposed network. The ModelNet 40 partial dataset is a synthetic dataset that contains object categories with large shape variations. The results show that our method is able to handle object instances with large shape variations, while the NOCs-based baselines cannot. Moreover, to quantitatively analyze how our method performs under different shape variations, we conduct an experiment. We generate several subsets of the lamp category in ModelNet 40 with different degrees of shape variations. We see our method generates results with high accuracy on all subsets, outperforming the baselines. We visualize the estimated pose by our method and several NOCs-based baselines. As shown in the figure, the 2 baselines have significant errors in estimating the pose of the object pointed by the arrow, while our method can handle these objects with better performances. Thanks for watching.